Okay, so we had a flurry of emails all weekend long. Everybody keep up with all that?
What email?
If you want to hear my sob story sometime, I'm going to tell you whether you want to or not. The last time that I taught this class, back in 2014, I used the Stats Portal, which is the same publisher, but their previous generation of this online homework tool. And it was full of errors, and by halfway through the semester, I was so frustrated with it that I just quit using it. And we turned in our homework on paper, and you waited and waited and waited for me to grade them. Well, the publisher assured me this time that we scrapped that. We just started from scratch. We got a new program. It'll be fine. Well, the very first homework set, we've hit 3 out of 10 questions that had problems. And so I don't know what's going to happen. Hopefully, I emailed it off to them over the weekend, and nobody responded today. So, yeah.
And then also sometimes they'll be like, continue, and then like a question will show up. So I submitted one without even knowing there was a third portion to the question.
I did that on
It doesn't
too.
Yeah, so I didn't know. I was just like, crap. I got like 1.8 out of 3. Like, how did that happen?
So what you're saying is that you saw on the screen a place to enter a thing, and you hit submit instead of scrolling down?
Well, it doesn't. You have to click continue, or nothing else will show up. So I clicked continue, there was a second portion, and then I clicked continue again, and nothing showed up. So I just submitted it.
Well, probably their server's just slow, so when you hit continue, you have to wait for it to load or whatever. Several people have said, and Courtney sent me screenshots of the thing, but several of you came into my office where you get this gibberish on the screen. Just back out of it and come back in, and usually it then works. So that's just loading slow, or it kind of freezes while it's trying to load the language. Yeah.
I was having trouble. I put in the right Z-score, and it would tell me I was wrong, and give me the exact Z-score that I put in was right into.
Yeah, and that was in the email that I sent out, and said, there's a bug in their error checking, and what they say. If you roll over, I don't know if you noticed, but when you enter, here we go. It'll have a little box. That's not the color I want. So, how about that? There's a box, and you enter a number in the box. And let's say you enter 1.99, which is roughly, I think they were negative, the Z-score you were getting. And then it says, like you missed it. Well, and then there's a question mark right beside that. If you roll the mouse over that question mark, it'll pop up a little box and show you what the correct answer was. Well, the answer they're putting in here doesn't match the answer that they put down there. And the answer they put down there is this one, right? And this one's like 3.84, something like that. Well, it turns out that this number is the square of that number. This is a chi-square test statistic, and this is a z-test statistic, which, as long as it's a 2x2 table, these two are equivalent. And the point of the problem was, hey, look, you can do this with the z-test. And you get the same results as a chi-square test, but they mixed them somehow, and Yep.
So how are you going to go back in and look at our scores? And fix
Well, I'm able to go in and see what you entered. So if I can see that you entered this, and it was counted wrong, then I just give the points back, which is a pain in the butt for me, because I got to do it on everybody's homework and all that. So it helps me if you email me and say that you're one of these people. Right? As far as I know, though, it's happening to everybody. Right? And so, And that's why in my email I tried to head this off at the pass and say, when you get this question, don't enter the Z like it asks, square it and enter that number, and it'll probably count you right. And so I don't know if anybody tried that or was successful at that. Yep.
I tried leaving off the negative. It hopefully work.
Yeah, and that didn't work either, did it? No. So anyway, we definitely have issues with the launch pad. Couldn't even remember what it was called there for a second. Yeah.
There was my business organization class. We had something from like Cengage, I think was what it was called. And that entire semester, it was a summer class, and it was like tech support every single lecture. She's trying to fix all the problems with the software.
Yeah, and I'm not going to do that.
We were getting so angry by the end of the course.
Yeah.
That's what, when you said, this is the first time they've offered this, I thought, oh, great.
Well, it was... Well, and the truth is, I don't feel like they were honest with me when they said we scrapped it and started over. Because the questions that are coming up, these are exactly the same. I think they just used the same question bank, but the overlying thing looks a lot different. But the actual air checking and all that, I don't think they started over. Yeah.
Also, I was doing that quick too, and I ended up finishing that and like getting a 100%. Well, I should have. But one of the questions, like I did a practice one, and they rounded to 1 decimal place. So then on the actual one, I rounded to 1 decimal place. But on the answer, it was 3 decimal places rounded. So I ended up getting 10 points wrong for that question because it was the same answer for all of them, just rounded.
So they told you to enter it a certain way.
There was no instructions.
Oh, no instructions at all. Yeah.
What to round it to.
I think she meant like the plus or minus.
No, it was...
yeah, I remember your email about that.
Probabilities. There was like 5 boxes, and they were all... Yeah.
I said around 3.
Yeah. So...
I was around 4 just to get that plus minus.
It depends on the question. Some of the questions are telling you what to round to, and that one apparently they forgot to tell you what to round to, but then they expected a certain way, and if you didn't happen to choose that way. So I think going to 3 decimal places is what they expected.
Some of them they do 1, though.
But some do specify 1. Yep.
So if we put in a more precise answer, are we okay?
No. That's one of my main gripes. And in my email, I don't know if you read the email that I had sent, I said it's unfortunate or something, I forget how I worded it, if they're marked wrong for being too accurate. You know, that seems odd. But anyway, we're going to deal with it. I'm going to see if I can get the problems fixed and all that. And if not, then we'll bail on it. Which, you know, I'll have some discussions with the publisher over that. And we'll see what we can do for you guys. But okay, so today is section 9.2, which is the goodness of fit test. So GOF is the goodness of fit test, and it is a chi-square test. We'll get through this a lot faster than the previous one because it's really done the exact same way as before. The difference is just in how that test is implemented. So goodness of fit, that phrase always kind of cracked me up as a student. Goodness of fit. And you have what are called goodness of fit tests. So how well does the data fit the distribution that you think that data comes from? So it's basically testing to see if the data is distributed in a certain way. For example, let's get out your calculators, your TI 83s and 4s, and rather than do it by handwriting here, I'm going to pull up a spreadsheet that I prepared in advance, and we're going to do some random number generation from our calculators.
That's impossible. We can stop now.
And I got to remember what I called it, though.
No, they're deterministic. There's no randomness to it. For the computer. Yeah, for a calculator. Impossible.
Okay, so this is an Excel spreadsheet that I created in advance. And across the top it says decile. Let me make this a little bit bigger. Decile. And do you remember what a decile is in data? Where'd my word decile go?
Scroll back.
Oh, that's column C, isn't it? There we go. Okay. So, a decile, you know what a percentile is, right? What's a percentile?
It's the percent of
You said you knew.
It's the percent below a certain number. So if you're like at the 50th percentile, there's 50% of the data below whatever number that is.
Okay. So be careful in the way you say it. A percentile is a value. Like if you're doing test scores, it's a test score that has 50% of the data below it. Or the 90th percentile has 90% of the data below it. Any word that ends in "ile" in statistics is chopping up the data into equal parts. Percentile is chopping up into 100 parts. Decile is chopping it up into 10 points. Quartile, 4 parts, right? So the deciles are 10th percentile, 20th percentile, 30, 40, and so on, right? So what we're going to do is we're going to have you generate, each of you, let's see how many we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. Ooh, perfect. Multiples of 10. I want you to generate 10 random numbers between 0 and 1. It's supposed to be a uniform 0, 1 generator. So let me get a marker. Yeah, I'll tell you in just a second. But so this is uniform 0, 1. And then we're going to look at the first digit after the decimal place. And my camera didn't follow me. Okay, so you're going to push. I got to remember where you go, but I think you go to the math button, which is above another button, isn't it?
No, it's just a button.
Okay, the math button. Then you go over to PRB for probability. And then under that should be the word RAND. There's all kinds of other random number generators in there, but we want RAND. And RAND is uniform 0, 1. So if you just say enter, it'll pop one of those up. All right?
You just want a real number. It doesn't matter. You don't want to.
I want to know.
Sorry.
I want you to produce a random number, which will be a number between 0 and 1. Right?
If it's like 50 decimal long.
It'll be 10 decimal long, probably. And I want for you to pick just the first digit after the decimal place. So what's your number?
0.1.
Okay, so you had 0.1 and a bunch of other stuff. His number is a 1. All right? So over here, we're going to get the observed counts where the first digit was a 0, first digit was a 1, first digit was a 2, and so on. All right? Now, if it's truly a random number generator, what would you expect for the counts of each of those?
1.
You'd expect them to be equal all the way across, right? A uniform distribution. Now I'm going to have each of you generate 10 of these, right? So we got 10 of you. Each do 10. That'll give us 100 numbers. Got it? And then I want you, just on your margin of your paper or something, to write this out like this and then put your count for each of those digits. How many zeros did you get? How many ones did you get out of your 10? How many twos did you get out of your 10? And so on. Right?
So there's no rounding. It's just the first number.
Just the first digit. You don't have to do any rounding. Just what is that first digit? Okay? And then I'm going to type in the sums of your observed counts. So you're going to have to help me do these sums as we go. And by the way, to do the next number, all you have to do is hit enter again. Once you do the first one, you don't have to go back through math, PRB, RAND. You just keep pressing enter and it'll give you a new one.
Or you just go second entry.
Then you can just use tallies, right? Just say zeros. I got 1, and every time you hit enter, put a tally under the number that you got. I'm trying to speed you up because you're obviously slow. You done, Brent? Okay. Did you have a question, Taylor?
No, I just didn't know who else to tell you.
Okay. Yeah, I'm ready, but I'm not sure the most efficient way to handle this. But let's just start with 0, and we'll go around and we'll add up how many we got, and then I'll type that number in. All right? So, actually, what did I do with my marker? What's that? Yeah, let me do it this way. Let's go 0, 1, 2, and so on. And then I'm just going to write down. So Nathan, you got what?
I have 1.
You just had 1?
Yeah.
Okay, and then let's go. Just start hollering them out. Jeremy, what'd you get?
I got everything that's 6 and 8 and 9.
No, how many zeros did you get?
Oh, 1.
1.
0.
0. 0.
0.
1. 2.
1.
1. All right, so we add all that up. We got 1, 2, 3, 4, 5, 6, 7, 8. So we got 8 zeros. Right? What? Oh.
Search in the corner.
Hello, camera. Come on, boy. Attaboy.
You tricked it. A little slow.
I'm too fast. Okay, so this has got to be faster.
Maybe you should just get one person to go across.
I know. Let's do this. The ones, raise up how many fingers you got, right? If you got 3 of them, you hold up 3 fingers, right? And then I'll just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's much faster. Now, 2s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 5s. 1, 2, 3, 4, 5, 6. That looks odd, doesn't it? 6s. 1, 2, 3, 4, 5, 6. 7s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 8s. Just 2? And 9s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So 9 wins. So Jeremy made the comment when I first started this, we can quit now because there's no such thing as a random number generator. These are pseudo-random number generators. And it's harder to do with this uniform thing than it is when we do random integers. But what you would notice is if you've never used the random number generator in your calculator before, you would all be in sync. You'd all get exactly the same number, and you press enter, and you'd get the same next number and the same next number. But as long as you're out of sync, but we should probably check that.
Explain us, maybe.
Were you matching?
Because we matched, yeah.
Okay. So this is a biased sample because I forgot before we started to make you get out of sync with each other. How would I do that? Yeah, you just press enter a whole bunch of times so that he's on the 20th time and you're on the 23rd time. Now you'll be out of sync, right? So the fact that you're matching, a lot of you are probably matching, is why we got odd results here. but that's fine. It still illustrates the point of this test. Do we have a sample of 100 numbers that are representative of a uniform distribution? Right? The eyeball test says, I don't think so. Right? Well, let's type these numbers in and use Excel to speed us along. Read them to me because I can't see them over there. How many zeros?
8,
8.
11, 10, 10, 14, 6, 6, 12, 2, and 19.
Okay?
That's only 98.
It's only 98.
Somebody was an amputee on their finger or something, and they didn't. I know I counted right. But that's 98. So that makes the next row a little bit tougher. Expected counts. But rather than go back and recount and see where the missing 2 are, except maybe, let's look at the 8s. How many people had 8s? So there really were only 2 8s? Because that's the one that's really sticking out as being odd.
Make it 4.
But-
Maybe we had 21 nines.
What's that?
Maybe we had 21 nines.
Yeah, possibly. So we'll leave it at 98, which makes this next thing a little bit easier. If we had 100, what would our expected counts be? 10, 10, 10, all the way across. Since we got 98, what's our expected count? 9.8, right? 98 numbers divided by 10 categories. If you expect it uniform, they all should be the same. So it's 98 divided by 10, or 9.8. So I'll fill in each of those cells with 9.8. And down here, does this look familiar? Quantity O minus E squared divided by E. That's the same chi-square statistic that we were doing last time. So O stands for observed, E for expected. So you take observed minus expected, then square that difference to make it positive, and then divide by expected, and then sum those up across all of the cells. Right? So before we had a two-way table. So we had rows and columns. In the goodness of fit test, it's only one row. And you have an observed row and an expected row. Before we had an observed table and an expected table. And we just went cell by cell. Same thing here, it's just all in one row. Okay? So each of these is the contribution of that cell to the chi-square statistic. So we sum all those up, and we get 20.57. Okay? Now, what's the next thing we have to figure out in order to compute a p-value?
Degrees of freedom.
Degrees of freedom. So how many degrees of freedom do you think there are? How did we do it when we had a two-way table?
We had n minus 1 times c minus, or rows minus 1 times columns.
Okay, rows minus 1 times columns minus 1. Well, that doesn't work here, does it? Because I only got one row. Rows minus 1 would be 0. We'll multiply that out, I got 0. But remember how we figured out the r minus 1 times c minus 1? I said, how many of these could I fill in before the rest are predetermined? It would be c minus 1, right? So it's just one less than the number of cells that you have, right? My observed count sum is a fixed number, and the sum here has to be the same. The sum of the expecteds has to be the same. And so I got to fill in 9 of them before I can figure out what the last one is by subtraction. So I'm going to have 9 degrees of freedom here. Right? So it's just columns minus 1. Or sometimes it's set vertically, so just number of cells minus 1. Okay? So if I put my cursor, I got these, it worked good for this problem that it was hidden from you until I'm ready to reveal it, but The reason you see these hashtag symbols is because I don't have my column wide enough to show the decimal places. But the p-value, if I click in that cell, I just typed in the number 9 for degrees of freedom, right? So L4 is the contents of this cell there, and I manually entered that it's 9 degrees of freedom. And so it's, let's see, I gotta get back down to that cell. Chi-square distribution, right tail from the contents of the cell L4 with 9 degrees of freedom. So the right tail means from that value, 20.57, out to infinity, what's the area under that distribution? Okay? Now, if I click on that cell, I used the automatic chi-square test function. Remember, I showed you that last time. You get a p-value straight from that also. You can get it either way. But notice that the two ranges that you enter. You enter observed range, which is just B2 to K2, one row, and then expected range, B3 to K3. Okay? And you get exactly the same p-value. So,
keep track of these every time you do this?
What's that?
I was just curious to keep track of these every time you do it to see.
From semester to semester? No. I have not done that. But the truth is, had we put you all in sync, or out of sync, on your random number generators, we probably would not have rejected. But what's our conclusion here? Reject the null. Okay. Now, I have this little soapbox that I get on because non-statistician researchers do this all the time. They quote p-values, and you ask them, what's your null hypothesis for that p-value? And they're like, what? You say, what are you rejecting? I'm not real sure. Don't ever quote a p-value if you don't know what it's rejecting or failing to reject, right? So what is our null hypothesis here?
That it is random.
Marker. Here you go. The null hypothesis for a chi-square goodness of fit test. For a regular chi-square test for association, the null hypothesis is there's no association, right? And the alternative is there is an association. Now we're testing the goodness of the fit, right? So the null hypothesis is the, quote, fit is good, right? Goodness of fit. So the null is the fit is good. The alternative is the fit is not good.
So how can you do it that way instead of... I feel like in statistics you normally assume that it's not, and then the alternative is that it is.
Exactly. And I'm glad you noticed that. So when we say fit, we also say the model. So I'm modeling this distribution with a certain known distribution. And does that model work? Now, what Taylor just picked up on was my next point. The goodness of fit test is backwards to the way we usually think of these things. Usually, it's the alternative that we hope to prove. The null is an assumption that we hope is wrong, and we hope to reject it. But this is flipped around the other way. We hope that our uniform distribution fits this data, so we hope to fail to reject. Right? So the goodness of fit test has some criticism from that perspective, in that it's pretty easy to fail to reject a null hypothesis by doing what? Come back over here to where we collected data. How could I have ensured that we failed to reject that? No? I mean, yeah, that might have worked. Get you all in sync. But instead of having you each do 10 numbers, do a smaller sample. Each give me one number, right? And so then I had, zeros and whatever, and ones for each of these. And then your sample size is so small that it's pretty unlikely you'd reject the null hypothesis. Right? Yep.
Can you explain the alternative being? Like the fit is not good. The distribution does fit.
Does not fit. Left a word out. I was just seeing if you were watching. Does not fit the data. Thank you. I wrote the same thing for the null and the alternative. Okay? Now, where this comes into play a lot of times in research, one of the places is like in survey research. We do, sometimes we do survey selection based on what they call proportional sampling. So you have something that is, quote, known to be true in the population. And of course that's never really known, but we know from the census, the last census drawn, that this percent of the population is male and this percent is female, this percent live in cities, this percent live on farms, anything like that. So then you say, well, now I want to do a survey and I want it to be representative of the population. So I'm going to stratify my sample on all those variables and do proportional sampling. So if there's 40% female and 60% male, I make sure my sample has 40% female and 60% male. And then, all those other things. And then you can do a goodness of fit test to see how well you did in your sample. Did I get the proportions I expected to get? All right? So that's basically what it's doing. You divide the chi-square goodness of fit test, you divide the data, whether it's categorical, whether it's continuous, whether it's discrete like this was. You make categories out of the data, and then you see, does the counts that I got in each of those categories fit what we would expect if the distribution I'm interested in is the correct model for this data. Okay?
So how does it know which distribution? I guess it doesn't matter because you're just comparing expected versus observed.
Yeah, but I want you to finish your thought because that was where I was going next.
Well,
how does it know? How does the test know whether you're testing for a uniform distribution or for a normal distribution or for some weird skewed distribution? How does it know? And your answer, you answered for yourself, is?
It's just observed versus expected.
The expected counts are entered based on what you would expect if this thing were normally distributed, or if this thing were, anything else. So here's an example of that. Each semester in my MA343 classes, I collect data from them. You guys remember doing this? On a lot of different variables, but one of the variables is resting pulse. And so this is the histogram from all the semesters that I've collected it through last semester. So there are almost 10,000 observations in this data set. It's like 9,900 and some. I forget the exact number, right? So think of it as 10,000 observations. Here's the distribution of pulses where each of these bars is, I believe, width 2. And I can actually go to the SAS code and see what they are. No, width 4. So I said, give me midpoints from a histogram from 36 to 124 by 4. All right? Describe the shape of that distribution.
Pretty normal.
Looks relatively normal. A little bit skewed to the right. The tail on the right side is longer than the tail on the left side. Right? And, just look at how steep it is here compared to how steep it is there. It's a little bit skewed. Is the normal distribution a reasonably good model for this data?
Yeah, that's it. Yeah, it's a large sample size.
Yeah, I'd say not too bad. But maybe we should use the chi-square goodness of fit test and see if this data fits what we would expect if the pulses were exactly normally distributed. Okay? So see if you can figure out the strategy for that. While you're figuring it out, I'm going to run a proc means. And by the way, you can do all these things with the SAS Enterprise. I'm using SAS Code because it's a lot faster for me. But here are the summary statistics. So there's 9,929 observations in that data set. The mean is 73.207 if I go to 3 decimal places. So the average resting heart rate is about 73 beats a minute. All right. The standard deviation is 11.130 if I round to 3 decimal places. All right? Now, let's do the decile thing again. With that mean, and let me write those down over here on the board, just so we can remember them. And we're going to treat it as if that's the whole population. So mu equals 73.207. And sigma equals 11.130. Right? So 73.207 for a mean and 11.130 for the standard deviation. Figure out the deciles. What? Somebody said something?
The min is 25. Doesn't have 25 each min.
That's a 36. Does it say, oh, yeah. The min was a 25. Yeah. And the max was 134. Both of those are extreme outliers and probably either data entry errors or big dummy errors. Right? Anytime you give a bunch of intro stat students a project like this, there's going to be people that just make up the data, right? And they really sometimes make up stupid numbers because they have no idea what pulse should be. So it's quite likely that 25 is either a data entry error or somebody just, well, I don't know, 25, and they made up a number, and then when you put it in the distribution, you can see, oh, that makes no sense at all, right? So there should be some cleanup of that kind of thing before you run any real analysis on data. But okay, so now I want to go back out to give me a board to write on. And let's fill in, well, I'll empty all these out. And then we'll come back and either, I don't know if I'll come back and fill in the observed counts or if we'll just do it within SAS. But what about expected counts? Decile. What would the first decile cutoff be? In other words, if the data is normally distributed with a mean of 73.207 and a standard deviation of 11.13, what would the 10th percentile of the data be? So, here's my normal distribution centered at 73.207. Halfway down the hill should be 11.13 less than that. So 62 point, I can't do the math in my head. Take 73.207 and minus 11.13.
Can we just use the inverse?
62.077.
How much? 0.077. Okay? Now, that percentile is what?
60.
What percent of the population should be less than 1 standard deviation from the mean? Or should be further out, should be less than the number that is 1 standard deviation below the mean? 16%. Right? So this is the 16th percentile. I want the 10th percentile. So I need a number that's a little less than 62. How do I get that number? Taylor, you started to say it.
Just the inverse.
The inverse norm. So if let's come over here. The 10th percentile, which we can label as P10, you can get off your calculator as inverse norm. I'm not writing very good today. Inverse norm of 0.1, comma, 73.207, comma, 11.13.
That's 58.9433.
58.9433. Okay? Then you do the same thing to get the 20th percentile, the 30th percentile, all the way up to the 90th percentile. And those are your 9 cutoffs for dividing the data into 10 equal parts. Right? So when I come back to the spreadsheet, what would my expected counts be? If I make the cutoffs for categories equal those deciles. Okay, I've stumped you all. So let's go back to my SAS program and look at... I'm going to run this little piece of program real quick and scroll up. So the deciles are listed here. I don't know if it's big enough for the camera, but this decile 1 is 58.94, and that's the number that Taylor read us a minute ago. So I just had SAS produce all of them all at once. Next one is 63.8398, 67.3704, and so on. The ninth one is 87.47. So what percent of the pulses should be bigger than 87.47? 10%. How many should be between 82.57 and 87.47? 10%. So if I use the deciles as my boundaries and I count how many people fell in between each of those boundaries, I ought to get 10% of the data in each of them, if the normal distribution fits very well. Understand? So I'll go back to my SAS program. Again, this is SAS coding, so if you're interested in coding and that kind of thing, then you can pay attention to how this works. But I just got a data set where I've merged on those decile values, and I have my pulse values. So each record, I got 9,929 rows of data. So for each data, I do an if-then statement. If their pulse is less than the first decile, dec 1, then decile equal 1. So each person, each row of data gets a value for this decile. It's either a 1, a 2, up to a 10, or what decile they fall in. Got it? Each of the deciles should get about 10% of the subjects. Okay, so if decile 1 is less than or equal to their pulse, and it's less than dec 2, then they're in decile 2. Right? So I'm just having SAS do it a lot faster than I can count by hand, 9,929 observations. Right? Then I'm going to create a frequency table of that variable decile. Now, how would you do this using the SAS Enterprise Guide? How do you produce frequency tables? That table analysis. You go to describe and then table analysis, and you only have one variable now, decile, so it's not a two-way table, it's a one-way table. Right? So you can do a one-way table. So decile 1, I got 684 observations. Decile 2, I got 967, then 1200, then 1600, then 900, then 1100, and so on. Right? Does that fit what we would expect? What's the expected counts? 10% of 9,929 would be about 993, right? So 0.1 times 9929. We would expect just a hair under 1,000 in each of the cells. This one's 684. This one's just a hair under 1,000. This one's quite a bit over. This one's a lot over. Right? Yep.
So how come you have a larger sample now? You have the 9939 instead of the 9929 or whatever. In your previous code, were you throwing out stuff that was in?
That's a good question. I didn't notice that before. Yeah, I've got 10 observations that aren't accounted for on that previous one. You know what I bet happened is my code has got a flaw in it. I didn't account for missing values. There's probably 10 people in the whole data set that didn't provide a pulse. And so what SAS does, unless you tell it better, is you say, if pulse is less than this number, well, a missing value is considered to be less than everything. So it would say, yeah. So it put all of them into decile 1, probably. So this number's probably 10 too big. It's already smaller than any other number in there, but... So what do you think? Just eyeball test, does it look like the normal distribution is fitting very well? Not really very well. But the pattern is odd, right? If it was a slightly skewed to the right, you'd expect, well, that upper decile would have way too many in it. It does. Well, not way too many, but it's got too many in it. Percent, it's got 10.5% instead of 10%. Right? But some of these, this one has 16% in it. Right? So what's interesting with data like this, again, particularly if people are making up data, is if you call your mom on the phone and say, hey, Mom, what's your resting pulse? And they don't feel like taking their pulse and actually doing it, what are they going to say? They're going to give you a number that is a multiple of 10, probably. They're going to say, oh, it's about 80, or it's about 70, or it's about 60, right? So the deciles that contain those multiples of 10 will tend to spike. It's one way of detecting fraudulent data, right? Is that you get more of certain values than you would expect. The big one that's fun to show, I've quit collecting it because it was just such a mess, is I had my students, I don't think you guys had to do it, but Brent, you might have, do body temperature. Do you remember doing body temperature?
I don't think so.
I did body temperature for a while, but boy, you talk about fraudulent data. Body temperature is hard to collect. Pulse is not too bad. You know, find your pulse, count 30 seconds. But if you want to get somebody's body temperature, you got to find a thermometer, right? So I made it optional. Say, well, you know, on at least one subject, you need to give me their body temperature, but try to get all 5, right? So most people were turning in all 5, but not really doing it. So what's normal body temperature?
98.
98.6, right? Guess what number had a huge spike in the data? 98.6 was entered more than any other number, and the distribution looks like this. And this is 98.2, which is really the average body temperature. They've done fairly recent studies, well-controlled studies, and determined that average body temperature isn't 98.6, like you've been told your whole life. It's really 98.2. So, but I get this huge spike at 98.6 because people are making up that number, right? So if you did a goodness of fit test on that for normal distribution for body temperature. There's no way the data would fit that. Here I'm getting some odd spikes. The graph, I didn't ask it to do this graph, it just does it by default. But it shows which of the deciles were too high, which are too low. It's kind of an interesting graph. I didn't point it out, but here's the results of the chi-square test. Here's the test statistic, 844.45, which is computed the same way we did it in Excel, with 9 degrees of freedom and a really, really small p-value. So it's saying the normal distribution does not fit your data, or better yet, your data does not fit a normal distribution very well. But with 10,000 observations, you have a lot of power to reject even small deviations from normality. So the eyeball test is a lot of times better. You just look at it and go, yeah, it's reasonably bell-shaped and symmetric, so that's probably fine. But the data, you have enough data to say, well, it isn't exactly normal, so I'm going to reject normality. So there's your chi-square goodness of fit test. And that's really all there is to it. So the homework over that will be due next Monday. So you've got a long time to get it done. But I'll be adding some more stuff as we do the rest of the week. All right? So you can head out. Check your email for the extra homework that I assigned that's due Friday. If you haven't noticed that in your inbox, it's there. It's using technology to do stuff. So we'll see you Wednesday.
What should we expect the grades to be?